In this video on specific heat, we're going to look at 7 different specific heat problems. After a couple of examples, I'm going to pause the video as I introduce a problem to give you time to work. Then I'll display the answer at the end. The first question reads, if the same amount of heat is supplied to samples of 10 grams each of aluminum, iron, and copper, all at 15 degrees Celsius, which sample would reach the highest temperature? Listed below are the specific heats of aluminum, iron, and copper. We actually don't even need to do any math here. If we write out the specific heat equation, Q equals mc delta T, we know that heat supplied, Q, is constant. That means that the product, mc delta T, also needs to be constant. We know that the masses are the same, m, so that term will drop out of the equation. That means the two remaining terms we're concerned with are specific heat and delta T. By that reasoning, the lowest specific heat should also yield the highest change in temperature. Copper, as you can see from the table below, has the lowest specific heat of 0.386, so with a very low C, it should yield a very high delta T. Another way to look at this is specific heat is resistance to change in temperature. A high specific heat will have a high resistance to change in temperature. A low specific heat will have a low resistance to change in temperature. So the correct answer to this problem would be the sample of copper. The next question reads, substances A and B are the same mass and at the same initial temperature. When the same amount of heat is applied to each, the final temperature of A is 75 degrees Celsius and B is 35 degrees Celsius. What does this tell you about the specific heats of A and B? This is really the same problem we saw earlier. Again, if specific heat is a resistance to a change in temperature, sample A went through a high change in temperature and therefore must have a low specific heat. Sample B went through a low change in temperature and therefore must have a high specific heat. So what does it say about the specific heats of A and B? Well, we don't know exact numbers, but we do know the specific heat of B has got to be higher than the specific heat of A. Let's now do a little bit of math. This problem reads, a 125 gram sample of an unknown metal requires 1.351 kilojoules of energy to heat it from 25 degrees Celsius to 112.1 degrees Celsius. Calculate the specific heat of that metal. As always, let's begin with our equation, Q equals mc delta T. I strongly encourage you to solve for the missing variable first by rearranging the equation, and then go through and plug in some numbers. Specific heat will be equal to 1.351 kilojoules, which we want to convert to joules, 1,000 joules per kilojoule. That's going to give us 1351 joules. All of that is over a mass of 125 grams, and a change in temperature, final minus initial, gives us a delta T of 87.1 degrees Celsius. Solving this out, we get a specific heat of 0.124 and units of joules per gram per degree Celsius. The units match, and we've rounded to significant figures. The next question says, the specific heat of gold is 0.13 joules per gram per degree Celsius. Calculate the mass of gold that can be heated from 15.2 Celsius to 20 Celsius by the addition of 1 kilojoule of energy. To start this problem off, we can again use the specific heat equation. Q equals mc delta T. This time you're solving for mass, and remember as well to convert kilojoules to joules. Now take a minute and go through to try to solve this problem. Pause the video now, please. The answer here around the significant figures should be 1,600 grams. This next question reads, during the winter, a pond containing 1.0 times 10 to the 5th liters of water cools from 12 Celsius to 5 Celsius. How much energy is released in this process? The keyword here is released. If we're adding energy to a system and the temperature goes up, we can use specific heat to determine how much the temperature will go up by. If a system is cooling and energy is being released, we can also use specific heat to tell how much the temperature will go down by. Specific heat works in both directions. So just like before, I encourage you to solve for the missing variable, which in this case we can do simply by writing out the equation. And then if we look at what values we have a delta T, which in this case will be negative. 5 minus 12 gives us a minus 7 degrees Celsius delta T. We know a specific heat of 4.184 joules per gram per degree Celsius, but we don't have a mass just yet. What we do have is a volume, 1 times 10 to the 5th liters, which we could convert to milliliters, and then using a density, convert to grams. This gives us a value of 1 times 10 to the 8th grams. Using those values, if we plug them in, we should get a Q value of minus 2.9 times 10 to the 9th joules. That's the energy released. By convention, a negative sign means released, but we could also phrase this as 2.9 times 10 to the 9th joules are released. This fourth problem says 225 joules of energy are released when 7.5 gram sample of iron cools. By how much did that sample cool? Use the problem above to work through and solve this question. Please pause the video now while you do your work. Did you get minus 67 degrees Celsius? Again, we're looking for a sample cooling, so we should see a negative change in temperature. We get that negative because 225 joules were released, so our energy is also negative. The last problem in this set reads, a mixture of iron and gold is heated evenly from 15 Celsius to 32 Celsius using 1500 joules of energy. What's the mass of this mixture? This is kind of an interesting problem because we have a mixture of two different metals. If you look up the specific heats of iron, you get 0.45 joules per gram per degree Celsius. And for gold, you get 0.13 joules per gram per degree Celsius. Iron accounts for 85% of the mixture, while gold accounts for the remaining 15%. Doing this multiplication out, we get these values, which if we sum them, sum to the specific heat of the mixture, or 0.40 joules per gram per degree Celsius. Take that value, plug it into the specific heat equation, and see what you get for the mass of the mixture. Again, pause the video now while you do your work. Did you get 220 grams? This question is a bit interesting in that, again, it's a mixture, and in order to calculate the specific heat of the mixture, we need to calculate the contributions of each individual metal. The iron accounted for 85% and the gold for 15%, so to find the overall specific heat, we take those percentages of the specific heats. Hopefully this video has been helpful. You have a better understanding of specific heat and a good understanding of how to solve these problems. Thanks for watching.